So this is lecture 3, example 2. And we're going to consider the sequence AN defined by AN equals 1 on 2n. So when n equals 1, we've got a half. When n equals 2, it's a quarter, a sixth, an eighth. There you go. And that looks like it's getting smaller and smaller and smaller. Our conjecture is that AN tends to 0 as n tends to infinity. So we want to prove that. And to prove that, we have to prove that the definition of converging to a limit of 0 holds. And that definition is, for every epsilon greater than 0, including little tiny ones, there exists some capital N, possibly a function of epsilon, element of natural numbers, such that whenever little n is greater than that capital N, then the nth value of the sequence is within epsilon, plus or minus, of that conjectured limit of 0. So once again, we want to prove there exists statement. In order to prove a there exists statement, a great way to do that is to actually construct the given n. So we're going to make a wild guess. We're going to choose capital N equals, well, before 1 on epsilon worked for a sequence which was more or less behaving like 1 on n. Now we've got a sequence behaving like 1 on 2n. Let's try 1 on 2 epsilon. Just try, see if it works. Once again, there's a little niggle for epsilon equals, pi or something like that. This capital N isn't a natural number, so I'm going to turn it into a natural number by taking the floor function of it, that is, discard any fractional part, just keep the integer, and then I'm going to add 1. And you need to think about it a little bit. That implies that if little n is greater than capital N, it will be greater than 1 on 2 epsilon. Okay, so what is the effect? Effect on the absolute value of AN minus our conjectured limit of 0. Well, that's the absolute value of 1 on 2n minus 0, which is just 1 on 2n. Okay, let's do a little, we want to conclude, we're hoping that this is going to be less than epsilon. Let's see if it's true. Let's do a little side calculation. Aside. Now we know that whenever little n is bigger than capital N, we are greater than 1 on 2 epsilon for that particular choice of capital N that we made here. Let's multiply by 2 both sides, if you like, or just flip it all. No, multiply by 2 both sides. That implies that 2n is greater than 1 on epsilon, and then we can take reciprocals. That's exactly what we want. So we don't even need to do any more algebra. We can directly say that 1 on 2n is less than epsilon, and that's exactly what we wanted to show. So actually, we're done.